The second video on exponential graphing, we're going to focus on the two features, the horizontal asymptote and the y-intercept. And previously we saw the general form that we're considering for exponential graphs. The final thing we touched on was the d parameter and the vertical translation d units up. So d units up if it's positive, so d being some real number, d units up, or down if it's negative. So it depends. So if it's -5, it's 5 units down. If it's +3, it's up 3 units from its standard position. We can see that on this graph here, the red line. That's I've just plotted 2 to the x, and if we have d set to 0, that is the graph of 2 to the x. If we have vertical translation up 4 units, it moves up 4, and say 1 unit down to -1, we can see there. So basically we can easily see the effect of that one. This is probably quite familiar to you because you've seen this type of translation with a number of functions already. At the moment you can see here that I've got d set equal to 0. So we can also see what appears to be a horizontal asymptote. We'd have to zoom in quite a lot to see that it's not actually touching that line y equals 0, i.e. the x-axis. If we zoom in a bit, we can see as we zoom in more, it's not actually touching. If we kept zooming in, we'd be able to see that in greater definition. But you've seen this phenomenon with other things like hyperbolas before, maybe the tan curve. So it approaches some asymptote without ever actually reaching it. We can also show that numerically by substituting extreme values in. What's important to notice at this stage is that we've got d set equal to 0 and the horizontal asymptote is y equals 0. So at the stage when d equals 0, we have an apparent asymptote of y equals 0. This means here that y equals d is the horizontal asymptote. So that's important to note. Alright, so sorry, that should be singular, asymptote. So that's one to note. So for example, without even knowing what the base A is, we know that this has a horizontal asymptote here at y equals -5, and something like y equals e to the x -1 would have the horizontal asymptote at y equals -1. Remember, lines like y equals -1 and y equals -5 are horizontal lines, and we've called them constant functions before, haven't we? So that should make sense based on all that previous work you've studied. Let's have a look at another one. If we've got y equals 2 to the x, plus 10, showing that one graphically, we know that it should have y equals 10 as the asymptote. Let's see with graphing software if we can verify that for us, and setting it equal to 10. There we go, and certainly appears that way, doesn't it? We can see on the screen that it's not much of a stretch to really see that that line there is the asymptote. Okay, so it's approaching that line. If we have extreme negative x value, so as x approaches negative infinity, we've got, it's not writing for me, let me try that again, as x approaches negative infinity, there we go, we see that it'll approach the line y equals 10 because we have a d of 10 on the end. Now, as far as the y-intercept goes, the y-intercept, like any other function, occurs when x equals 0. So if we look at y equals 2e to the negative 3x minus 5, let's try that algebraically and check it with some graphing software. So when x equals 0, we've got 2e to the negative 3 times 0, so that's 2e to the 0. E to the 0 is 1, so 2 times 1, or 2 minus 5, and we have negative 3. So it should cut through the y-axis at negative 3, and if we look at the graphing software, yes indeed, we can see that that's where it cuts through. So that's nothing new, and it all works as usual with exponentials. Next thing and final thing here is when we're plotting exponential graphs, it's important to use a significant point. A significant point is something that's easy to substitute and does the job at showing distinction between curves. So it's especially useful for when we're comparing curves or sketching graphs. And so x equals 1 is an example. It's a really good example of that. Don't use x equals 0 because that is reserved for the y-intercept, as we just said. Okay, but x equals 1 is the other really easy thing to substitute in. And when we've got some examples here, 10 to the x, e to the x, 2 to the x, we all know that now that we've got that exponential shape, we also know that they'll all go through, because when x is 0, something raised to the power 0 always gives 1, so they'll all go through 1 on the y-axis, the y-intercept. But what happens after that? If you substitute x equals 1, it's easier to substitute, alright, and you'll also get a good hint about how well the curve initially curves upward. So 10 to the x rises up quite steeply. If you substitute in 1, 10 to the 1 is 10, and we've got the point 110. E to the x, not so much. E is about 2.7 roughly, and 2 to the x less so, and you get an idea. So that's an important step. The idea is to choose a point that's easy to substitute in and does the job at showing distinction and showing the